Introduce our speaker for today's seminar, Professor Andy Tolmie. He is Chair of Psychology and Human Development at UCL Institute of Education, where he has been based since 2007. He is also Deputy Director of this Centre for Educational Neuroscience. He's a Professor of Developmental Psychology, researching neurocognitive and social factors underpinning the growth of children's conceptual representations and behavioural skills in real-world settings, for example, the acquisition of road crossing skills. His work is primarily education-focused with an emphasis on primary school science, but also recently the role of motor control in the development of executive function. Previously editor of the British Journal of Educational Psychology from 2007 until 2012, he's currently an associate editor for Brain Sciences and Frontiers in Psychology in the Cognitive Science section. And finally, he is the chair of the research board for the British Psychological Society. So today he is going to be talking to us about his research into science learning in children and the role of causal cognition and spatial-temporal processing. So I am now going to hand over to you, Andy, and turn my mic and camera off.
Great, thank you, Rebecca. I will start by sharing my screen. Get that up first of all. Yeah, I'm going to be talking a bit about some of the work that's I've been involved in for the last few years, actually, on causal reasoning in science is really the kind of core of it, but in particular the role, evident role, as I'll go on to explain it, of spatial temporal cognition in that. And more recently, things to do with, well, particularly attention is something I want to touch on today, but also things to do with scientific vocabulary, which may sound like rather a mixed bag, but hopefully will make sense by the time we get through to the end of the talk. I want to start, though, by offering big acknowledgements, first of all, to firstly Selma Dunda-Kirker, whose PhD work with me is really the kind of foundation for this, and much of what I'm going to be talking about to begin with is based on work from Selma's doctoral thesis, published now in a variety of different outlets. But also thanks to Tom Northrop, who I'm pleased to see in the audience here, who did his MSc dissertation with me last year, and one of the studies I'm going to be talking about a bit later is based on was Tom's MSc work. And also I'm going to talk about the work of Dasha Berga, who was another of my MSc students last year, at the final part of today. So thank you very much to all of those. We wouldn't be here today without their help, that's for certain sure. So that's important to acknowledge them. So what I want to do to start off with really is to just say a little bit about science learning itself, because I don't want to kind of assume too much in the way of background knowledge here. Indeed, you know, I think I've learned one thing over the last 20 years or so in working in this field is that science learning has not been a major focus of attention for that many people. So I think I always feel the need to rehearse something slightly of what we're actually looking at here. So let me start by just saying a little bit about what we see as being the key elements of science learning. And this is based in part on a review paper that I did with Zova Ghazali and Sue Morris back in 2016. So the overarching focus of science learning, I think, is on causality. It's about understanding causal processes as they occur, causal events as they occur in the external world, and thinking about how those events actually come to be. So that's the kind of core of thinking about science, and that requires attention to certain types of information. So first of all, in order to actually understand anything about causality, you've got to be sensitive to data relating to different types of causal process. So in other words, you've got to notice that there are things which follow other things. So in other words, there are kind of putative causes and events that follow on from those causes, and be sensitive to those kinds of connections between those events. But going beyond that, obviously in terms of science learning, but science as an enterprise more generally, this requires capturing data in explicit form in order to be able to anticipate, predict, report broader patterns in these events as they're witnessed. So this is going to be noticing things like the factors that seem to be involved in causal events, and maybe going beyond that to thinking about variables. So for instance, in the context of objects sinking in water, you may notice that on the whole is not the only parameter. That weight seems to have something to do with it. Heavier things are on the whole more likely to sink than lighter things. But that in itself is something that underpins a variable of weight, potentially as some kind of dimension that is influencing the outcome in those kinds of events. And we can identify this in any kind of context. So basic factors and then ways in which they vary to lead to different outcomes. That's a kind of bookkeeping view of science up to that point. I think real science depends integrally, though, on being able to understand something about not just what factors and variables are actually associated with particular types of causal outcome, but thinking about the kinds of mechanisms that actually make those processes, those outcomes actually happen. So what is the connection between the cause and the outcome? And then we might want to think about this as indeed will for children as being some kind of fairly undeveloped understanding, but something that is about the kind of sense of what is going on that's leading from one thing to another. But eventually, of course, this is the foundation of some kind of theoretical understanding of science. This is the basis of theory as an understanding, essentially, of mechanism. And then there's another strand, which I put in square brackets, not to kind of hive it off, but to mark that we tend to think about this as something separate. So there is a very important strand in doing science around being able to generate and assess evidence to ensure that our understanding is accurate. And that type of skill is generally referred to as scientific thinking. There is a tendency, and I think for good reason within the literature, to see a distinction between science and knowledge, which is really the first part of the things I've been talking about, and science as a kind of task, as a way of doing things, and that distinction I think is quite valid. So I kind of hive scientific thinking off. At least in this kind of preliminary part. I will return to it at the end, but as seeing it as something that's a bit distinct from this kind of understanding, particularly of what's going on in causal events. But as I say, I'll come back to that a little bit later. So of all those things, what we've argued for some space of time really is that this understanding of mechanism is really central to being able to do science, learn science effectively. And there's reasons for that, which are kind of part of what I've said already, which is, the theoretical nature of science, that understanding of mechanism is really the kind of the foundation of being able to develop scientific theories and being able to understand things in that kind of way. So it's central in that kind of sense. It's also central because it's actually quite complicated when it comes down to it. And this is really, in many senses, the focus of what we're going to be talking about today. So in terms of natural systems, whilst it is kind of tempting to think of effects immediately following on from causes, so that when one object strikes another and the second one moves, that is a kind of seen often as a kind of archetypal causal event. But in actual fact, most natural processes are not of that nature. Typically, they involve an temporally extended continuous process. So when an object sinks, for instance, even if it's a really heavy piece of metal, there is still an appreciable amount of time involved between the object being placed in the water and actually hitting the bottom of whatever it's sinking through. So there is a kind of extended process there. When objects dissolve in or soak up water. Again, these are things which I'll illustrate this in a moment. Is things which take place over time, and so it's not necessarily very easy to identify. First of all, what is actually happening, but also, as Piaget observed in the Principles of Genetic Epistemology, very influential text, I think, chapter there on causal understanding. That grasp of mechanism, because of this temporal extension, because the the processes that are actually involved are in many senses invisible. In order to grasp mechanism, what you've actually got to be able to do is to engage some form of mental simulation and projection of that simulation of underlying unobservable time-based processes. So he gives the example of the electrician or the electrical engineer throwing a switch and seeing the light come on, but in actual fact, the electrical engineer understands far more about what are the actual sequences that's involved, completely hidden between the switch being thrown and the light coming on. And it's that kind of understanding that we're trying to get at here. How do children actually come to understand that, and what factors actually play into that? To kind of underline the point about how important this is, how essential this is, without wanting to get ahead of the story here, we've found certainly preliminary data that understanding a mechanism in this kind of way, being able to see something about what that process underneath the surface actually is a good predictor of performance on the kind of standardized science tests used as part of the TIMSS international measurements studies at grade 4. So there is a direct relationship between this kind of understanding and general performance in science. So that's a further reason to see this as kind of being central. So going back to Piaget and something of what is actually involved here, the kind of point is that we have a separation between the observable and unobservable factors or processes, sequences that are involved in any kind of causal event. So, for instance, we take the simple event of a child throwing a ball and it being caught by his father. Then there are observables in terms of the kinds of people involved, the objects involved, and a certain amount of information about the kind of visual pattern that is presented by the ball as it's thrown and then caught. But of course, none of that in itself actually relates to the processes or shows directly the processes that are involved in that, in terms of the force of the throw, leading to travel in one direction, air resistance against that force of throw, and gravity trying to pull things down. And a proper kind of sense of what's going on in throwing a ball involves understanding of all those forces and the ways in which they interact with each other to produce the trajectory that's classically followed by an object in motion under those kinds of circumstances. So what we're talking about really is the advent of children's ability to be able to understand and get at these unobservables. And what we've argued, I'm going to go right back into the kind of basis of the argument, but what we've been arguing for some time is that central to that is what we call spatial-temporal thinking, or spatial-temporal cognition, which we define as basically the ability to extract information from states over time and to use that information to construct dynamic representations of change. So if you think about the ball throwing example, it's about being able to track what the trajectory is and to be able to infer something about what is actually, whether with support or not, be able to track the observables and to infer something about what must be going on in order for the ball to follow that kind of trajectory over the period of time through which it's in motion. So what we're arguing is that the spatial-temporal ability, the spatial-temporal analysis, provides a link between observations of continuous processes and their analysis in terms of underlying causal mechanism. And it's that perception and inference from observations which we are arguing provides a foundation for wider science achievement. And ultimately, as I'll come on to a little bit later, grasp of experimentation as a central part of that. Okay, so let's look at some of the kind of basic studies that have been done on this by Selma as part of her PhD work. I'm not going to go into a huge amount of detail about this, but what I want to draw out is what we've found so far about the kind of the important influences of this hypothetical spatial-temporal ability and what seems to be kind of distinctive about it. So let me show you first of all what the kind of tasks involved look like. I'm going to focus here on one of the 3 tasks that Selma used as part of her studies. So this is the absorption task. And you see we've got 2 strips of paper here. On the left-hand side, we've got a piece of blotting paper. And on the right-hand side, we've got a strip of tissue paper. And these are both dipped into a shallow tray of water. And as you can see, what happens is that, that the water rises up through the paper and actually continues to do so after it's been removed from the water. But it rises more rapidly in the tissue paper than it does in the blotting paper. So in the kinds of tasks that we've used, what we do is we present contrasting instances of this kind to children to kind of get them to focus on the process itself, because it's different in different instances, and what's going on that makes a difference. We ask them, first of all, we show them the event that is going to be examined. We ask them to make a prediction about what they think is going to happen. We then show them what actually happens and ask them to describe explicitly what they've seen. And then we ask them to explain what they've seen. Why did things turn out the way they did? And in those explanations, what we're looking for really is, at a very basic level, can they identify the factors that are involved? The tissue paper is thinner, more flimsy than the blotting paper, for instance. Can they transfer that into a kind of understanding of variables? So it's a matter of the comparative difference between the 2 pieces of paper that leads to the difference in the rate of absorption of water. But crucially, none of this is actually really an explanation. What we're looking for is the kind of higher level explanations where they can say something about why it is that the tissue paper allows the water to ascend more rapidly, which is essentially something to do with the openness, greater openness of the structure, allowing the water to rise up more rapidly through it. So that's what we would term, at rudimentary level, admittedly, but that's what we would term as being an understanding of mechanisms, showing some awareness of what is going on that is actually leading to the difference in outcome. So that's the kind of thing that we do for the causal tasks. And then to measure spatial-temporal ability, compare performance on this to ability to extract that kind of causal mechanism. I'm just going to talk about, we've used a few different tasks, but I want to focus particularly on 2. So the first one is this task called the flow of liquid, which was taken from Piaget's work as well. And basically in the flow of liquid task, what happens is that at the outset, children are presented with a flask of liquid in the array seen on the left. So there's an upper flask and a lower flask. The top one contains a liquid, there's none in the bottom one. There is a tap in between, and the water is let through in stages. And what they're asked to do is, on a pro forma of the kind seen on the right-hand side, they're asked to mark the level of water at each stage. And then once they've done that, the equipment is put to one side, the drawings are taken, they're shuffled up, and then they're asked to put them back in the right order. Still not the crucial part of the task. The crucial part of the task is that then the drawings are actually cut in half along the dotted line there, so that the tops and bottoms are actually separated from each other. They're all shuffled up again, and now they're asked to put the drawings back into the correct sequence. And we look at that in terms primarily for younger children, in terms of the accuracy with which they can actually do that. So that's the flow of liquid task. There's another task that we've used, which we call DTV, distance, time, velocity. And basically this is a task which is derived from work by Wilkening back in the 1980s, updated in terms of presentation. But basically what happens here is that the children are presented with scenarios in which they're asked to calculate distance on the basis of time and understanding of velocity, to calculate time on the basis of distance and calculate speed on the basis of time and distance, and to calculate velocity on the basis of time and distance. complicated. So we present scenarios of each of these kinds, and we look at the accuracy again of children's performance on these. So that's the basic kind of measures of spatial temporal ability that we've used in that research. I'm going to cut straight to the results, really, because this is really a kind of crux of this. Across 2 studies, what we found, as is shown in these path diagrams here, is that there is a really quite strong relationship between this the kind of spatial temporal tasks and the ability to engage in the kind of causal reasoning, the extraction of mechanisms that I was talking about previously. And in particular, what we see here is that this is the results from the second study. What we see here is that there seems to be a kind of configuration of basic non-verbal ability in terms of performance on a block design task, which feeds into the distance time velocity task and the flow of liquid task, and those then feed into causal reasoning performance. But essentially what we're seeing is that the effects are all kind of being mediated to a very large extent through the flow of liquid task. So there is something about the flow of liquid task which seems to be particularly predictive of that kind of ability. And up in the upper right there, possibly not very legible to you, you can see from the results from study 1 showed a very similar picture, and the only difference really was the role of vocabulary, which I'll say more about in a moment. But so essentially what we're seeing is that flow of liquid task in particular, but also the DTV at a kind of more mediated level is explaining causal reasoning in the way that we kind of anticipated that might actually be the case. And if we look at that further in terms of how children's performance related directly to different levels of performance on the causal task, we see that actually perfect performance on the flow of liquid task, being able to get a perfectly accurate score on that to solve it without any problem at all, seems to be a necessary, if not a sufficient condition for being able to identify mechanisms. So in terms of identification of mechanisms, every child who did that passed the flow of liquid task perfectly. High percentage in terms of being able to coordinate variables as well. Whereas those who were at lower levels of performance on the causal task were not particularly likely to have performed above chance level on the flow of liquid task. So there's a significant pattern of effects here showing that, as I say, that the flow of liquid task performance on that seems to provide a necessary foundation for the kinds of identification of causal mechanism we're talking about. And we also found that the DTV score was higher too for those who were able to identify mechanisms. So there does seem to be some clear evidence of a strong relationship between spatial temporal ability of the kinds that's assessed by the flow of liquid and the DTV tasks, and this identifying the capacity to identify causal mechanisms. That's a very top level view of a lot of data. There's much more that could be said about that, and indeed, you know, much more that we've actually done, which I really will just touch on very briefly now. Firstly, to say that that particular task flow of liquid seems to be a consistent predictor of understanding of mechanism, not just in children, but also in adolescents and adults. We've looked at performance at all different ages on this, and we found consistently that this comes up as a predictor. In terms of the different age ranges, it's accuracy for children that is the kind of determining factor. So a fair percentage of children will not do well on that task in terms of accuracy. Adolescents and adults will usually get to an accurate response, but the time that they take to do so is predictive of their ability to identify mechanisms. So essentially, you know, those who solve the task very quickly have an understanding that seems to be associated with understanding of mechanism, whereas those who solve it slowly don't seem to have that ability. We've tried to unpack this in various ways. What's going on here? Why is this predictive? We've certainly found that performance on the flow of liquid task is predicted in part by visual spatial working memory using various tasks, sequence reconstruction tasks, block span or 1-out span. But interestingly, the bit of performance on flow of liquid that is predicted by visual spatial working memory isn't the bit that predicts causal cognition. It's separate from it. So you find that that even when you partial out the working memory aspects, flow of liquid is still strongly predictive of causal performance. We check that across 2 studies now. You might think that it's something to do with the kind of logic involved of as the top level goes down, the bottom level must go up, and that seems reasonable. Piaget devised this flow of liquid task originally as what he called a double seriation task, so there was a kind of logic there. We found that performance on the flow of liquid task doesn't actually seem to be particularly related to seriation ability, so it's not apparently anything to do with the logical sequence, or not the simple logic of that anyway. What in particular the relationship to the DTV task seems to suggest is that it is genuinely some kind of measure of the capacity to mentally simulate, not perceive a sequence, but to mentally simulate it in terms of change over time, and to derive some kind of underlying principle which is governing those observations. And what seems to be going on perhaps is that the DTV is a less strong predictor than the flow of liquid task. Its effects are mediated by the flow of liquid because it's capturing it's capturing something around the simulation ability, but not necessarily something to do with the kind of derivation of those underlying principles. So that seems to be perhaps some kind of key dimension. But really the kind of, where I want to go to with this here is that there's still much that we don't really know about what this ability is and why it's actually why it's having that kind of predictive effect. So good spatial temporal performance doesn't seem to guarantee mechanism inference, but it does seem to suggest there is something integrally important there, which needs to actually be applied to the context of particular types of causal observations in order to actually generate those kinds of representations. And clearly, what we need to understand is what is it that's actually kind of critical as a driver to that. So it doesn't seem to be anything to do with general verbal or spatial ability on its own. Both of those have an effect, but they're only, on our data, only associated with performance on the causal tasks at lower levels. So being able to identify factors and variables seems to be related to those. Being able to identify mechanisms doesn't in general seem to be related to that, which suggests that it's something to do with that temporal dynamic aspect that's actually the critical dimension. But it remains to be demonstrated that it is that temporal dimension that it's more central than spatial. And also, I think it's less than clear really from what I presented so far, what the specific route is by which spatial temporal analysis of this kind leads on effectively in the end to influencing scientific causal reasoning. And one dimension that we've been interested in here is that of scientific vocabulary. So general vocabulary doesn't seem to be particularly important in understanding scientific phenomena, being able to capture those. But what we have found in past work is that scientific vocabulary, the ability to use more specialized terminology, seems to predict higher levels of causal reasoning. And one thing that we've been thinking about there is that it may be that's because it allows the kind of dynamic representations created by this spatial temporal ability to be indexed in some kind of way that can make them somehow more manipulable, more applicable to fresh events. So that is certainly a dimension of interest. What I want to do to kind of further part of this talk is actually focus on the studies that were done by Tom and by Dasha, which examine really both of those dimensions and provide us with, I think, some important further insights into what might actually be going on here. So to start with Tom's work, first of all, this was focused really very much on the role of attention. And what we were interested in here was whether attention to and encoding of spatial temporal attributes of visual scenes was something that explained variability in causal reasoning. So is it in a sense a basic attentional process that's at the core of what's going on here that makes spatial temporal ability an important predictor of causal reasoning by facilitating the observation that actually then drives the derivation of representations. So this study was done, of course, in the middle of the pandemic. So it was done online, And it was done with adults because it was difficult to capture any of this with children. But as I've already said, I think it's perfectly appropriate to think about these things with adults because the same pattern of effect seems to obtain in adults as obtains in children. So this was a small adult sample, 18 in total with full data, data collected online, and tasks implemented in Gorilla, which took Tom, well, he learned a lot about how to program in Gorilla as part of that. I think it's fair to say it was a lengthy process, but it ended up with some really good materials. So I'll say a little bit more about the tasks in a moment, but there was also a self-report on, in particular, science achievement. So how well did participants consider themselves to have done in science at school, and also professional engagement. Do they have any engagement with science in terms of their occupation currently? In terms of causal reasoning, we use the absorption task that I showed you earlier, and we focus really just simply on the explanations that participants were able to provide for that. So essentially, what kind of level of explanation could they provide? And then the kind of core of the study was really this spatial-temporal attention measures, using a detection of violations paradigm. So basically what this involved doing was tracking the movement of an object behind an occlusion and then identifying if it appears at the right point and the right time. So to illustrate that a little bit more, this task was based on a task that was used as part of EEG work, actually, ERP work by Doherty et al. And that in part was actually the initial interest as well, to think about how this might be form the basis for subsequent EEG measures, but we'll put that to one side for the moment. So basically what happens is there's a fixation period on the screen of 450 milliseconds, and then a helicopter starts to move across the screen on the left-hand side, moves behind an occlusion, and then appears the other side of that. And what participants were asked to do was to press a space bar on the reappearance of that to give them a reaction time. So how quickly could they register that the thing had actually reappeared, with a supposition that if there was some kind of temporal or spatial violation, then they might be slower to actually do that. And then that was followed by a question on whether the place and time at which the helicopter reappeared was as expected. And they underwent 12 trials, each with no violation, spatial violation only, temporal violation only, and both spatial and temporal violations. And what we're interested in, as I say, was really their reaction time and their ability to track accurately those violations. Were they actually able to detect them? And what we found was that there were no differences, in fact, in the end between condition in terms of reaction time. So I won't say more about that, but it was certainly striking that detection of temporal violations was substantially poorer than detection of spatial violations. Though it got better, they were more accurate at detecting temporal violations when they were accompanied by a spatial violation as well. So it's like they're kind of, it's easier to recognize a spatial violation that somehow is more perturbing. And if you notice a spatial violation, then that helps you notice the temporal violation as well. But if you've just got a temporal violation, then people seem to find it quite difficult to actually register that that's occurred. But the crucial point was that it's that ability to detect the unaccompanied temporal violations we found was the only predictor of causal reasoning, with small sample, but the beta was high, and there's quite a substantial R squared on that as well. So this does seem to be really quite an important dimension. So temporal attention, the ability to detect temporal violations seems to be, in terms of causal reasoning, more discriminating as well as harder. And of course that makes sense perhaps in terms of what I was saying before about how we'd found that spatial ability only seemed to predict lower levels of performance on causal reasoning tasks. And it was the spatial temporal ability that seemed to kick in at the higher levels. And it suggests that it's this temporal sensitivity that is really perhaps the kind of crucial underpinning dimension there. And interestingly, we also found that temporal sensitivity was associated with self-rated science ability and science occupation. So there just seemed to be, that's self-report data, but it does seem to be that there is some kind of tie-up here between a temporal sensitivity, science, previous science performance, occupation, and ability to actually engage in detection of causal mechanisms, causal reasoning on current tasks. Okay, so it looks like temporal attention might actually be a fairly crucial dimension. So at the other end of the spectrum, what happens after that? And this is where Dasha's work comes in, looking specifically at the role of scientific vocabulary. What Dasha did in this particular study was to examine the relationship between causal reasoning, spatial temporal ability, and use of scientific vocabulary. And this was an adolescent sample. And again, this was conducted during the pandemic. So this was all done via one-to-one video sessions, a sample of 38 from years 10 to 12. So there were two causal reasoning tasks, both related to projectile motion under different conditions of gravity and air resistance. So basically, the contrast effect here was, the motion of a projectile when it had been fired at a 45-degree angle on the Earth or on the Moon. So you've still got gravity, but you've not got an air resistance. And then in contrast in the second task between being fired on Earth and being fired in space, where gravity is also now reduced substantially, as well as the removal of air resistance. So as in the kind of classic form of the tasks that we used previously, the participants were asked to first of all predict what they thought was going to happen, describe what they actually saw. These were obviously not real events. These were animations of the events, not having the capacity to actually kind of film events in space really very easily. And then finally to explain what they actually saw. And in terms of the scientific vocabulary measure, Dasha used the same approach as Selma and I had used previously, which is essentially looking at the use of terminology in responses to the causal reasoning task. So how far did they use specific types of scientific term within their responses to that? And so looking really essentially at the frequency of those things. And then the spatial temporal measure was a relative arrival task, which was based on the task that Selma had used previously as well. And we also took a measure of generic nonverbal ability, which is a task called the design organization test, which I'll not describe in any details. It's very closely related to the block design task, which is this paper and pencil version of, rather than involving manipulations of the blocks themselves, as you may be familiar with in that. So to kind of give you a little bit more on the tasks themselves, so you can see on the left-hand side here, the kinds of differences that were seen. I think this is contrasting Earth and Moon, if memory serves me right. So you can see that the trajectory is much shorter and much shallower on the Earth, the top level, than it would be on the Moon. And they basically had to understand that difference would be there and to be able to describe and explain it. And then the speed task, the relative arrival task, is shown on the right-hand side. And basically, this involved three rabbits of different colours racing towards a carrot because they're hungry. You can tell that this was originally devised for primary school children. And basically, they start from slightly different positions, they move at slightly different speeds, and then the motion stops before they get to the carrot. And what the task involves is over a series of items, is actually being able to accurately detect which one would get to the carrot first via extrapolation of what's been seen in terms of the motion up to that point in time. So you can see there's a kind of resemblance there to Tom's violations task, detection of violations paradigm. Okay, what did we find? Sorry, no, not for that, scientific vocabulary. So the kinds of terms that came out of that, I mean, given the kinds of restriction to projectile motion that the tasks were kind of focused on, you can perhaps understand that the kinds of terminology that we use were obviously of that particular ilk. But that's the kind of the type of terminology that we were looking for and counting. So essentially, how often did students use this term? Okay, what came out of that? Well, going to present this in terms of the kind of regression models, first of all, that Dasher generated from this. And you can see the basic hierarchical regression pattern here was that the design organization test, the generic non-verbal ability was entered into the model first, followed by the spatial temporal task, the speed task, and then scientific vocabulary to see what actually happened to the pattern of explained variance and the betas when we do that. And you can see, I think, a really very consistent pattern here, that essentially that the non-verbal ability is actually to some extent predicted when it's entered on its own, but as soon as the spatial temporal task performance is entered, then that typically falls away in terms of its influence, mirroring the pattern that I showed you earlier in that path diagram from one of Selma's studies. So spatial temporal seems to take over from more generic non-verbal ability, but as soon as you put in scientific vocabulary, in this particular sample, the effects of spatial temporal seem to disappear, which was kind of interesting because we've never actually seen that kind of pattern before. But then the work that we'd done previously on scientific vocabulary suggested that was with primary school children. It was suggestive, but perhaps, at an earlier stage in development, that was harder to capture the effects here. I think the kind of the crux of this really is the mediation analysis that Dasher did to follow up on that, to see what was actually happening. And basically what comes out of that is that it's not the spatial temporal ability isn't having an impact on the ability to identify mechanisms. It's that the effect of that is entirely mediated through scientific vocabulary. So in an adolescent sample, there seems to be a strong channeling of that ability into derivation of scientific vocabulary. And it's, in a sense, the kind of combination of those things conjointly, which is actually predicting causal understanding. Okay, so what we can perhaps conclude from that is that taken together, those studies, I think, provide at least some support for the argument that basically helping us to understand the sequence of what's involved here, the spatial temporal ability rests specifically on attention to temporal detail, first of all. So temporal detail and observed phenomena is attention to that temporal dimension that seems to be critical. And the argument is that then facilitates the construction of dynamic representations of those causal processes. If you're good at the spatial stuff, you can get static representations, but that dynamic representation requires attention to the temporal detail. But once you've constructed those dynamic representations, you need to be able to apply and manipulate those to events as you witness them. And what we argue further is that the encoding of those representations using more specialized dedicated vocabulary, generic vocabulary won't do it because it's too kind of multitasked, if you like. There's too many nuances of meaning. We need dedicated vocabulary to support the specific encoding of those representations and their applications to specific instances of causal observations. So that's looking more like the kind of sequence of what's actually going on here in terms of why spatial temporal ability is actually associated with identification of causal mechanisms. Some educational implications, I think, come out of that, which are really very important. First of all, something that we've been arguing for some time is that causal reasoning actually draws on imaginative non-verbal processes, the ability to construct these dynamic sequences which are not verbal in themselves. They may become specialized, encoded through specialized vocabulary, but they are essentially non-verbal in origin. And it's the capacity to actually imagine these things which seems to be the kind of start point for proper engagement with science. And what that argues is that science activities in primary schools in particular need to support the development and application of that non-verbal ability, in contrast to what typically happens now in primary science classrooms and secondary science classrooms too, where the focus is on science literacy and being able to use the words and being able to talk the talk, if you like, but not actually being able to imagine what's actually going on underneath the surface that is actually generating those kinds of events as we witness them. So focusing initially on non-verbal ability, constructing those kind of dynamic representations, and then at that point linking that through to scientific vocabulary as a means of actually manipulating that. And I'll not go into detail here, but we ran a very preliminary kind of intervention study looking at this, which seemed to suggest that that kind of effect was a very substantial one, a very real one. So ultimately, I think what we're arguing is that the crucial educational goal is to support accurate mapping between these observational regularities and inferred causal mechanisms. And this is really where scientific thinking comes in. It's about being able to accurately observe down to the kind of, in particular, the levels of temporal detail that are involved, the rate at which things happen. It seems to be really kind of particularly crucial in noticing the rate and what might be inferred then on the basis of those differences in rate. To just add a word on that in passing, an observation that was made by one of my other PhD students many years ago, Sharon Phillips, looking at children's performance on the balance on a balance scale task, and finding that children very frequently engaged in a process of gradually manipulating the weights on the balance scale and watched the rate of which the beam fell if it wasn't balanced, in order to kind of see what direction they needed to move the weights in order to make it balanced. And I think that was an instance of exactly the kind of process that I'm talking about, that it's that capacity to actually notice the rate, infer things on the basis of that, and use that to make manipulations. And I think it's that really that ultimately underlies the ability to engage in experimentation. So I think the other thing that comes from this is that in many senses what happens in much primary science is that it's got things the wrong way around. It kind of focuses perhaps too much on the kind of process of scientific thinking and not enough on being able to generate the kind of imaginative understanding of dynamic processes that underlies that. And it's this combination really that's needed, and especially needed in order to provide a foundation for secondary school by establishing some sort of sense of the theory evidence relationship. Thank you. That's me. Let me stop sharing.
Thank you, Andy. That was really interesting. Has anybody got any questions for Andy? You can put them in the chat, or you've got some applause, Andy. You can put them in the chat, or you can raise your hand and ask them out loud. Matt has a question. Go ahead, Matt.
Thanks for the really interesting talk, Andy. So I was, you were describing like spatial-temporal dynamic representations for understanding causal phenomena. Do you think there's a difference between those, understanding a causal representation and spatial-temporal association between change of two things? Or
yeah, I mean, I think we've tended to take spatial-temporal ability as something which has more kind of general applicability. So you can analyze the spatial-temporal sequence of an event without there necessarily being any kind of particular causal process, or not in any very salient sense, a causal process involved in that. So, you know, of course, as soon as you say that, it becomes hard to think of examples. But yeah, I think the kind of the key thing is that when you're focused in particular on the causal events, you're looking at it at a level of detail that's a bit different. So it's not just mapping the sequence; it's understanding. The point that I made talking about the flow of liquid tasks, it's about understanding something about kind of the principle involved. So it's not just about there being a sequence of change. It's about understanding, in some sense, you know, putting it in Piagetian terms, the kind of necessary relationships which actually underpin that would lead to a causal outcome. So it's a refinement. It's not quite the same thing. I mean, I think, you know, the spatial temporal dimension seems to be crucial, but adding in something specifically about the more closed system that's involved in a causal process seems to be a step beyond that, which is why you get that pattern of relationship between flow of liquid and the causal task. There's a step more that you need to do, which is something about applying, I think, that kind of ability to an analysis of the observations that you make when you're observing a causal event. This is pretty new stuff, and there's not very much out there about this. So
Thank you.
Necessarily a level of speculation involved at the moment.
Cheers.
Does anybody else have a question for Andy in the chat? Oh, Irini, since temporal relations are so key, how do you teach those abilities and skills in children? How do you boost them?
Yeah, great question. And quite a challenging question in a way. I mean, I think the start point for me, I mean, I don't think we know too much about that as yet, and it requires more work to actually tease that one out. But the kind of preliminary intervention study that I was talking about, what we did in that, this was with children in years 1 to years 3 in a school in a very deprived area, actually. So there was not high expectations of performance here, and what we did was to present them, first of all. It was all focused on object sinking and floating, and what we did was to present them, first of all, with a kind of demonstration event in which a stone sank rapidly in a big tank of water, and a big tomato went down and then bobbed back up again. And what we then did was spend 5 minutes or so getting them to actually talk about the detail of what they'd actually seen. And then once they'd done that, we asked them to engage in an imaginative game where, in threesomes, where one would be the water, another one would be the stone, and another one would be the tomato. And they were asked to simply, on the basis of what they'd seen described, to talk to each other about what they were doing to each other in order to actually lead to these outcomes. You can do this kind of thing with 5-6-year-olds. Try doing it with 10-year-olds, you might get a different response. But a very, very interesting thing happened, and unfortunately we didn't have the resources to track the longer term effect of this, but within the next 10 minutes we got them to talk about their ideas, and then we got them to reapply those ideas to a new set of objects, and within the space of 10-15 minutes we were getting consistent mechanism type explanations. We were getting accurate predictions. They had been sensitized to something by that process. Now, whether that was actually genuinely impacting on temporal attention, I think is something that remains to be seen. But there is certainly a proposal that we've had in development for a while that would actually help to perhaps unpack some of that. That's the crux of it. I don't have a better answer than that at the moment. I think getting children to focus on what it is they observe, though, and I think one of the problems in the way that's not intended to be a criticism of primary science teachers is because I think of the way that science as an enterprise is commonly framed educationally, that they tend to focus on presenting descriptions of what's going on rather than saying, just focus on the observations. I'm not going to tell you anything about what's going on here. You just tell me what you're actually seeing. And I don't think there is that kind of emphasis on attention to observation that is needed. The interesting thing, as I say, from the balance scale example, is that children seem actually sometimes quite capable of generating that attention themselves, but they don't seem to see that as being something which is valued within the school setting, perhaps for the reasons that I talked about.
Thanks, Andy. That leads actually quite nicely into the... Oh, sorry, Irini, did you have a follow-up on that? No. But yes.
Okay.
Oh, we can't hear you. I see you're talking, Irini, but I can't hear you.
No, I said no follow-up. Thank you very much, Anna.
Okay.
That was very good.
Okay,
Thank you, Irini.
So yes, this leads nicely into Chris's question, actually, which is how much, oh, Michael asked a question and it disappeared, hold on. How much do these results depend on a child's experience in the physical world? How might use of computer simulations as substitutes for real world demonstrations affect the development of these skills? So it's kind of two separate.
I have long had a kind of feeling that the observation of the detail of real events is probably pretty crucial, at least as a kind of initial stages of development. But I think really, in the sense that what that boils down to more is how good are the kind of animations and how salient is the information that's actually being presented with them, and does it actually present the right kinds of things? So, and how far do children actually trust those? I say that in part because though I have this kind of idea that somehow the physical events and noticing the nuances of those is crucial in the work that Rebecca referred to earlier on children's road crossing skills. The intervention work that we did there used simulations because it was just too kind of risky to have children running around roads really without the kind of the degree of control that would really prevent them from learning anything. So we did use simulations for that, and interestingly we found by having relatively schematic simulations that focus really on the key details that actually that those were really very effective, and what's more, the performance on the simulations accurately measured subsequent performance on the roadside. So I think it is possible to do things with simulations, but they've got to be focused on the right things, and I think that's not necessarily such a straightforward thing to do. I think busy high production value animations are probably not the way to go here. I think that's too much information, and it's not kind of identifying the salient information. So I think you can do this with the right type of simulation, but it's that takes careful thinking about the design.
Right. I wasn't trying to be critical of the method of testing.
No.
It's more that, in my experience, I've seen ninth grader. I'm here in the States in Baltimore, and I've seen ninth graders come into a classroom and see, I don't know, we have this cartoon, Roadrunner cartoons, where the Roadrunner hangs suspended in midair and then drops down. And even ninth graders said, "You mean that doesn't really happen?" So, they have, and I'm realizing with a lot of sheltered, especially during COVID, a lot of sheltered children that don't spend a lot of time in the real world understanding the nature of gravity and mass and effects of weight and air, that they lose a lot of that if the science classroom ends up showing too many of these simulations where they can't tell the difference between that and some inappropriately scientific, quote, scientific video. But yeah. Thanks. No, I think using them in the assessment is fine. I was wondering how it might have affected development based on experience of the children.
No, I think it's really important, and I mean I think if you were going to use simulations, absolutely grounding them, keep bringing them back to real observations. I think as far as possible is important. Okay. And they've got kind of halfway house there on video as well, which might also serve a role, as long as we can be sure that it's not being adulterated in some kind of fashion.
Thank you.
Thanks, Andy. We've got time for one more question, which is from Michael. So he says that you've highlighted the role of observing the rate of events to build an accurate representation of dynamic causal processes. A lot of more advanced scientific understanding is about invisible causal processes, e.g. electrons flowing along conductors. How does this dynamic, time-sensitive aspect of causal understanding extend to visualizing invisible causal mechanisms?
Great question. I'm not sure I have a very kind of polished answer to that one. I mean, I think it's partly about, of course, information received. I think that's always going to be part of it. So it's perhaps about being able to actually with assistance decompose events into things which might actually be important dimensions. So things like electrons moving. But I suppose the kind of the other thing that you might be wanting to kind of focus on there, which is related to that kind of sensitivity in the same kind of way, perhaps, is, you know, I mean, battery circuits perhaps are better than other types of material for demonstrating something that's where you can notice that, you know, the kind of sometimes, you know, with longer wires, there is some appreciable, very small, but still appreciable gap in time between the battery connection being made and the light coming on, which suggests that you know, that there is something to be paying attention to here. So it's supportive, I suppose, of the notion of there being some kind of flow, that there is some kind of temporal dimension to that. It's not instantaneous, which was the kind of, you know, Piaget's example, I suppose. Well, all the causal relationships that we're talking about really are invisible. I mean, the kinds of forces that are involved in objects floating and sinking are intangible, in the sense that, you know, you can't actually see their operation. You can see the consequences of their operation. I think it's about building a kind of sensitivity, I suppose, to the fact that there is something going on that actually needs explanation, and then supporting the process of inference as to what what it might actually underlie the sequence that's being observed. The rate of change does seem to me to be fairly kind of critical as a source of information. It tells you something about the process, I suppose, that might be involved in that, in terms of its power, its kind of you know, the kind of imbalance, I suppose, in the context of sinking of forces. I don't know. I mean, I think, you know, this requires a lot more exploration. But it does seem to be that that's at least a kind of key dimension to it.
Thank you, Andy, for your talk and for all your responses to the questions. We are over time now, so I'm just going to once again say thank you and do my little applause thing.
Thank you.
So yes, this is recorded if anybody wants to go back over it, and they'll be uploaded on the YouTube channel in due course, not immediately, but soon. So thank you, Andy.
Thank you. Thank you, everyone. Cheers.
Can I ask a question before you go, Andy? If you've got please feel free to say no and go and enjoy the sunshine. Is there so I'm thinking about a situation where a teacher is explaining